In the first part of this course, we're going to introduce logic, and we're going to start talking about deductive versus inductive reasoning. So in this video, we're going to define terms associated with logic. We're going to use Venn diagrams to determine the validity of deductive arguments, and we're going to use inductive reasoning to predict patterns. And we're going to look at the differences between deductive and inductive reasoning. So first, let's just talk about logic in general. Logic is going to be the science of correct reasoning. We use reasoning every day. We're talking about mathematics, or we're talking about any kind of argument you're giving to anybody, or if you're just getting information from the world, we use logic to parse it out and to make conclusions based on it. It's a fundamental part of our existence, and it's what makes humans different than other creatures in this world. We're going to break this logic, this idea of reasoning, into two different things, deductive and inductive. We're going to start with deductive reasoning. So deductive reasoning is going to be the use of a general statement to say something about a specific example. We're going to use some theory or some pattern that we already know to get information about a specific example. So because this is a math class, we should start out with a really mathy example, and note that this is going to be the most mathy thing that we're going to do in the whole first chapter. So first example, find all solutions to the equation x squared equals 2x plus 1. That is, we're finding all values of x that we could plug into that equation so that it could be correct. So what we're going to do is we're going to use deduction to figure out this question, the answer to this question. So we know that because x squared equals 2x plus 1 is a quadratic equation. It's quadratic because it has a squared term in it, and it's a polynomial and has an equation. Then we can use the quadratic formula to solve the equation. The quadratic formula says that if you have any equation of the form ax squared plus bx plus c equals 0, with the first number there, the first coefficient, not equal to 0, this can be solved using the equation x equals negative b plus or minus square root of b squared minus 4ac over 2a. So this is our general theory, our general statement that we're going to apply to our find the solutions to x squared equals 2x plus 1. Using the general to go to a specific. So in order to use this, we actually have to put our equation into the correct form. Right? The general theory says that it has to be specifically in the form ax squared plus bx plus c equals 0. And right now, we do not have that form. But if we subtract 2x and subtract 1 over, then we put x squared equals 2x plus 1 into the form x squared minus 2x minus 1 equals 0. Then we can apply this quadratic formula. Now it's in the right form. We have in front of the x is a hidden 1, in front of the x squared, I should say. In front of the x is a negative 2, and the constant term is negative 1. So a is 1, b is negative 2, and c is negative 1. So if we plug those values of a, b, and c into the quadratic formula, and we simplify, we get this as 2 plus or minus the square root of 8 divided by 2. And note that even to get from that first step to that 2 plus or minus square root of 8 over 2, we're using even more general theories that we have applied to the specific example. We know that if we square a negative number, it becomes positive. So if we square negative 2, that becomes not negative 4, but positive 4. We know that if we multiply numbers, we can multiply more than one number at a time. If we take the negative of a negative, we get a positive. These are all general sort of theories. We're applying to specific examples, and we're deducing what the answer should be. To go further, we can simplify square root of 8 to get to 2 root 2 by rewriting 8 as 4 times 2. So square root of 8 will be square root of 4 times 2. That is square root of 4 times square root of 2, 2 root 2. And again, each step along the way, we're using a different theory. Then we can cancel out a 2 out of every single term, and we're left with 1 plus or minus square root of 2. So the point of this example is not to be able to use the quadratic formula, even though that's something that we should be able to do, and that's a nice skill. That's not what you're going to be tested on in this class even. It's just what logical arguments are we using to get to our final answer of 1 plus or minus square root of 2. And there's a big general one we're talking about, the quadratic formula, but even in simplifying our answer, we're using many different general statements to get specific examples. We are deducing what the answer should be. So let's look at a not math example now. We are going to prove the fact that Michael Jordan, we're talking about the basketball player here, not the actor, is an athlete. And I'm not saying that Michael B. Jordan, the actor, is not an athlete, but let's talk about the other one. So our general statement that we're going to be looking at is that all basketball players are athletes. That's the general idea. And if we know that Michael Jordan is a basketball player, then our conclusion is that Michael Jordan has to be an athlete. We apply the general statement that all basketball players are athletes. Michael Jordan is one, so he's also an athlete. And this form is what's known as a syllogism, and it is comprised of three different parts: a major premise, which is our general statement, our general kind of theory, our pattern that we know; the minor premise, which is our specific example; and a conclusion, what we're actually trying to say at the end. And this comes from Aristotle, which is one of the earliest logicians, and he pioneered the use of this syllogism, this form of reasoning, and it was used for a long time past that as well. It really wasn't even until the 17th century that this notation we're going to introduce in the next video was used. We started going away from this syllogism format of reasoning. So one that he wrote famously is, "All men are mortal. Socrates is a man. Therefore, Socrates is mortal." We have a major premise that all men are mortal. That's the idea that we're using. The specific example is Socrates that we're looking at. Therefore, Socrates has to be a mortal person. So all logical syllogisms, if we try to kind of reduce this into a certain form, can be written as if A, then B. That's our general theory, our general pattern. If something, then something else. We have our specific minor premise that X, some specific thing X, is A. And that means that therefore X is B. And we can use Venn diagrams to illustrate these logical syllogisms. Note that on the previous page, if you go back to the Michael Jordan example, if A, then B is if someone is an athlete, then, did that backwards. If someone is a basketball player, then they are an athlete. And we're saying Michael Jordan is a basketball player. So therefore, Michael Jordan is an athlete. All logical syllogisms can be brought to this form. And again, the Venn diagrams help us to understand these. So let's talk about the Venn diagram real quick. We're always going to start with this rectangle or square. We're going to label that with a U. And the U stands for the universe. We don't have to get all philosophical. It's not necessarily the entire universe. It's just whatever we're talking about. So if we're talking about all people, then the universe is people. If we're talking about, all exam grades in a Math 107 course, then the universe is going to be that. And it can change depending on what our situation is. So that's what the U stands for, is just saying everything we're talking about is going to be included in this rectangle. Then we have different circles that represents different sets of what we're talking about. So A and B are different things, athletes and b-ball players, among other things, right? Men and mortals. And we're going to look at how these two circles interact with each other. So we're going to do that in kind of 4 different ways with 2 different sets. The first is what we're going to call the universal affirmative. And that is that all A are B. So that's the idea that like all basketball players are athletes. So the basketball player is what we're going to call our A. So we can label this A with that circle with the basketball player. And the athletes are what we're going to call the B. Since the circle A is entirely in the circle B, that means that all basketball players have to be athletes. If you have some X in here, right, if the X lies outside of that circle A and inside that circle B, then you're saying that person is an athlete, but not a basketball player. Maybe this X is like a swimmer or something, a different kind of athlete. But if you have X be somewhere else, then that might be a specific person like Michael Jordan, who is a basketball player and an athlete, so you're in both circles. That's what we call the universal affirmative. The reason why we say universal is because of the word all. We're talking about all things at one time. And we're talking about affirmative because we're saying a positive statement. As opposed to the next one, we talk about universal negative. It's universal because of the no. We're saying there's not anything going on. We're saying a general statement. But since it's negative, it's a negative thing. So no A, R, B, universal negative. We have 2 circles, A and B, representing different things, and they are completely disjoint. They're not touching each other. You can't have a point in here that is a part of both A and B. These things are nothing alike, and we'll see an example of that in a little bit. Then we get into the particular affirmative and negative. The particular affirmative, our keyword here is some. So we're not talking about all basketball players, we're talking about maybe some basketball players have a certain property, or some men have a certain property. But here, some A or B means that these 2 things are not one completely inside the other, but they are intertwined in some way, that they overlap in some way. So here we have A and B, and if we're talking about some A are B, then we're saying that if there's a point in here, and we call that point X, that X is in A and it's in B. That means that some A are B. Whereas if we have a point here for the not, then we're saying that X is in A, X is part of that, but X is not in B. So we're going to use these Venn diagrams to help us with a few examples in the next few pages. And we're going to use these terms, universal affirmative, universal negative, particular affirmative, particular negative, to help us out with the logic we're going to go through in the next few sections. So let's see an example. We're going to try to analyze some deductive arguments, these logical syllogisms, and we're going to see what pops out. So our first one we talked about, all men are mortal. Socrates is a man, therefore Socrates is mortal. So we put this in this kind of form, this if-then statement. We're saying if we have men, then they are mortal. If A, then B. Then we're saying Socrates is a man. So we're saying that Socrates is A. And then therefore, Socrates is mortal. B. And we're going to call Socrates here is our X, is our specific thing that we are talking about. So in our Venn diagram, we have our universe. We have a circle for mortals, right? So the universe might be mortal and immortal creatures. We have a circle for men, and men are completely inside of mortals because of that first statement. This is a universal affirmative. And since Socrates is a man, it has to be inside that circle with men. So therefore, we know that Socrates is mortal because the X is inside of the big circle as well. All right, so this argument checks out. It makes sense logically. We're all good to go. We're going to see some arguments that don't check out in a little bit here. So the next one, we have all doctors are men. That's our major premise. That's if doctor, then men. The minor premise is my mother is a doctor. Therefore, my mother must be a man. So the point of this example is that this argument is logically sound, right? All doctors are men. If my mother is a doctor, therefore my mother is a man. It's really kind of the same thing that we had in the previous page, replacing mortals with men and men with doctors in the previous page. If all doctors are inside of the circle with men, and my mother as a doctor has to be an X, and X has to be a man as well. So logic is fine. However, the conclusion is obviously incorrect. And that's because the initial hypothesis, this major premise that we're using, the general statement or theory that we have to make this deduction is invalid. And so therefore, this argument is invalid. It's not true. And really, this is getting into arguments in general, or just differing opinions on things, or differing arguments for different ideas in politics or religion or just everyday life. Many people argue validly. Their arguments are valid, but their major premises that they have are different. And sometimes there's not, a universal truth that everybody can agree on. The major premises might be more subjective, and because of that, our arguments contradict each other. So in that case, the argument may be valid, but the conclusions are different, and that's where a lot of disagreements happen. And really, that's politics in a nutshell, is that two factions have different major premises, so therefore they have different conclusions, even though they have logically sound arguments. Luckily, in math, there is no variation, there's no ambiguity in the major premises. They are things that are universal truths that we use, so therefore the logic is sound all the way down the line. We can deduce the correct thing. So let's look at another argument here, and this one's also not going to be valid. Let's see what the issue is here. So all professional wrestlers are actors. That's our major premise. That's our theory that we're using. Our specific is that The Rock, Dwayne Johnson, is an actor, right? And both those two things you could say are true. Professional wrestlers are actors. Sure, The Rock is an actor. Yeah. Therefore, The Rock is a professional wrestler. And if you don't know much about Dwayne Johnson's previous life, or before he was an actor so much, he was a professional wrestler. That is true. But this argument is invalid. The conclusion is valid. The argument is invalid. And to see why this is true, you can replace The Rock with another actor like Tom Hanks. And you could say all professional wrestlers are actors. Tom Hanks is an actor. Therefore, Tom Hanks is a professional wrestler. And we know that that's just not true. And what the difference is that where you place X in this Venn diagram makes a difference, right? So here you might have The Rock. He is in both circles. That's great. But there's nothing stopping us from having our X out here, that might represent Tom Hanks, an actor who's not a professional wrestler. So the form of this incorrect argument is if A, then B, then we're going to say that X is B, so therefore X is A. And that is not correct. We need to say that X is A, and therefore X is B. So even though you may get the correct conclusion, it's the argument that is incorrect. Right? And we can see this happens all the time in a typical math class, like an algebra class, where a student might get the correct answer, but they really didn't do the correct things to get it. It's like doing two wrongs, don't make a right. Even though you might get the right answer, you're not doing it in the right way. You could say it's almost lucky that we got the right answer in this one. So another example, we're going to talk about the particular affirmative and negatives now. Some plants are poisonous. Broccoli is a plant. Therefore, broccoli is poisonous. So let's think about this. Since we have the particular, we're going to talk about these overlapping circles, right? There are some plants that are poisonous. So this middle part, change the color here, this middle part here represents plants, poisonous plants, plants that are poisonous. Then we have this section over here. Those are plants that are not poisonous. And this part of the circle over here are poisonous things, but not plants. And it depends on where we put broccoli, our X, that makes this argument possibly invalid. So X is a plant, but there are two places we could place that X. You could place the X in the plants not poisonous section, or in the plants that are poison section, in the overlapping section, or in the part that's not. And if we think about X in the left side, that's a correct argument. We're saying that broccoli is not poisonous in that case. So here I'm going to say, in this first example, this shows us that broccoli, if I could spell it, broccoli is not poisonous. But over here, we're saying that broccoli is poisonous. And it depends on where we put our X. And because there is some way that we could put the X that makes this not true, this argument is invalid. We're not going to have any ambiguity, any leeway in our argument when we're talking about deductive reasoning. It has to be absolutely true or it doesn't work. So one more example dealing with deductive reasoning. We have no snake is warm-blooded. That is true. All mammals are warm-blooded. That is also true. So therefore, snakes are not mammals. So this is our universal negative idea. We have snakes and warm-blooded circles are completely disjoint from each other. They are not going to overlap at all. There is no snake that is warm-blooded, so there's no overlapping of those circles. Then we have our universal affirmative. All mammals are warm-blooded. So that is saying we have a circle inside of warm-blooded that represents mammals. It's a subset of warm-blooded things. And therefore, snakes, if you have any X value here, anything in this circle, call it X. It has to be within that circle, therefore it can't be in the warm-blooded circle, it can't be in the mammal circle, so therefore that is a true syllogism. It's a valid argument that we're making. The Venn diagram helps us visualize why that's true. So, thinking about deductive reasoning, we know that we can't have any ambiguity. A has to lead to B, has to lead to C, has to lead to D, and there has to be reasons why we go from one point to the other. And this is what we do a lot in math, is we have these rules, we have these general theories that we apply them to particular problems, and that's why we say there's only one right answer in math, is because these general theories tell us that we have to go from here to here to here to here. Inductive reasoning, however, is much different than that. Inductive reasoning, we go from a specific example to a general statement. We're going from a minor premise to a major premise. So, unlike deductive reasoning, the conclusions made with inductive reasoning are not guaranteed. Deductive reasoning, there's no ambiguity. You have to go from one step to the other. The conclusion is guaranteed. Everything is good to go. With inductive reasoning, you can only just say, at best, something is probable or something might be possible. And this is what we use to develop theories. And it's very important in its own right. It's just different than deductive reasoning. And we use inductive reasoning all the time in our lives as well. So let's look at an example of this. Major premise, Joe sneezed after petting Franco's cat. Another premise, Joe sneezed after petting Paulette's cat. So therefore, we could say that Joe is allergic to cats. If he sneezed after petting one cat, he sneezed after petting another cat, we could just say that Joe is allergic to cats. We're using specific examples to gain evidence as to why something might be true. And we're seeing that we're going from specifics to a general statement. So premises are rather evidence to support a conclusion, but just because you pet two cats and you sneeze doesn't guarantee that you are allergic to cats. Maybe you are allergic to dust, and dust is present when you touch both cats. Or maybe you are sick or something, and that's why you're sneezing. So, with enough evidence, you could say that it's very probable that Joe is allergic to cats, but you can't say it for sure. So inductive reasoning is very useful when we're trying to develop a theory, we're trying to find out what is true, trying to figure out a theory, which is used all the time in science. That's our scientific method idea. And it's very useful when conclusions just cannot be guaranteed, which is the case a lot in real life as well. And if we have limited data as well, that can be very useful inductive reasoning. So we often think about inductive reasoning as pattern recognition. You're given some evidence as to why a pattern might be true. Maybe you're thinking about, a number pattern or something in your everyday life. You use that evidence to say something about the next number or the next day. So let's talk about just finally deductive versus inductive reasoning. In your everyday lives, you use both deductive and inductive reasoning. When you're trying to make an argument, you'll use both deductive and inductive things. But they are very different and they have very different kind of uses. Deductive reasoning goes from a general theory that you can use to apply to a specific example. That might be a very mathy thing like the quadratic equation, or it might be a very simple kind of if-then statement. Whereas inductive reasoning, you start with specific facts and you try to develop the theory. With deductive reasoning, it is guaranteed to have the conclusion be true, and that is not true with inductive reasoning. In fact, you can never be guaranteed the conclusion is true. You can only say at best that it is probable. Deductive reasoning, we use a verified pattern or theory to conclude something specific. Inductive reasoning, we use specifics to hypothesize a pattern or theory. And this is the basis of logic in general. And we're going to explore these ideas for the rest of the first chunk of this course.